Okay, I thought I would make a short video on creating a MathCAD sheet to solve for the stresses and torques and power requirements and everything for a lead screw, or in this case a power screw, more like a power screw. I'm going to use the screw here in this 3D printer. This is an Ender 3 3D printer, and it uses a stepper down here, little NEMA 17 stepper motor connected with this coupler to a lead screw, and it uses that to raise and lower the z-axis. So if you were to turn, it will raise or lower, and so that's how it controls its motion in the z direction anyway. And so that's the one we're going to analyze. I fully do not expect any sort of stress that's going to be anywhere near the yield strength of this. This is a stainless steel rod, or screw, so I don't expect anywhere near that kind of stress. But we'll calculate it just so we can see how that does work. There could be some power requirements on this motor being able to raise this gantry at a certain speed. Normally the z-axis doesn't move very quickly in a 3D printer, but there are some movements like z-hop in a retraction type setting where you're trying to pull the filament out and move the carriage up really quickly and then move to a new spot to start printing, trying to reduce some of the oozing and strings that might occur, and you want that motion to be pretty fast. And we could actually calculate at least a theoretical maximum for how fast we could do that based on these calculations. So I'm gonna open up a MathCAD sheet we have right here. I have it started. This is actually, let me get it out of the way before it falls off the table. And let's look down here instead. So we'll have to look at both of these things. So the screw, the lead screw, is actually a trapezoid. You couldn't by your eye tell a trapezoid for an Acme, but I happen to know that this is a T8, so a trapezoidal. It's 8 millimeters. It's a quad start, so there are 4 interlaced threads on here, and it has a pitch of 2 millimeters. So that gives it a quad start, 2 millimeter pitch, gives it 8 millimeters of lead, and the thread profiles are trapezoidal. On here, I've got a picture of an Acme on the top and a trapezoidal on the bottom. They look identical, except the Acme has a 29-degree included angle, and the trapezoidal has a 30-degree included angle. So slightly, ever so slightly different in the two of those. So we have this bottom one is what kind of screw that we're dealing with here. All right, so let's put some information in it. I already said some of these things. So starts, it has 4, pitch, and the pitch, just so we're 100% sure we know what we're doing here. The pitch, we would go in, and it's going to be really hard with these tools at this scale, but we would go in and try to find one point on one thread and the corresponding point on the adjacent thread. And we're off the screen, but doing that is pretty much right on 2 millimeters. So here would be 2 millimeters, and you could kind of see, it's in the dark a little bit, but you can see that from one edge to the next edge of the next thread is 2 millimeters. So that's our pitch. So we can calculate. Oh, I'm on the wrong screen trying to type. There we go. 2 millimeters. We can calculate our lead is our pitch times the number of starts that we have. So this is a 4 start. Let's put that in millimeters. I'm going to go ahead over to the side and define these variables in terms of what our equations in the book use, so that the P and the L will show up correctly. Our mean diameter, or major diameter, not mean, major diameter is 8 millimeters. So that would be, if we took and measured across the outer part, we'd get 8, and I'd get 7.98. So that's pretty much 8 millimeters. our root diameter is, I would have to try and measure in between. It's actually easier. I don't know if I can show it very well on the camera here just because of the proximity of everything. It's actually easier to measure it right on the end down here. I can't really get this without it blurring out on us. It won't zoom. Yeah, there it goes. See how there's a circle on the end? We can measure that to get the root diameter. And it turns out that when I measured it before, it was 6.7 millimeters for the root diameter. And we already knew alpha. Remember, though, that the degrees shown here are 30 degrees, and alpha is 1/2 of that. So alpha is only 15 degrees. All right, so that's good. Let's move that up there just to have it nice and neat. We need to know the friction between this rod here and the nut that it rides in. I should have pointed that out, but there is a little brass nut that is connected to all that gantry, and that's what is moving up and down. So we need the friction coefficient between stainless steel and brass. So I looked that up on just type in stainless steel on brass or steel on brass friction, and you get two frictions. There's a lubricated and a dry. So we're going to assume that you have lubricated this, and it's 0.19 or so. We'll go ahead and take a note, though, that if dry, F is equal to around 0.5, and it depends, it's going to be a range of numbers, but we're taking the worst case scenario stuff. We could probably make this 0.2 and have a little bit more conservative estimate. All right, now the force. We need to know how much force we're lifting, and I measured the gantry, and the mass of the gantry is 1.5 kilograms, more or less. And I took the upper end of what this would weigh, so that's the mass of it. So the force that we're having to lift is going to be the mass times acceleration due to gravity, so 15 newtons ish. And then we go into our torque to raise and lower equations. So torque to raise is, now I've already typed this equation in, so I don't think I want to type it in again. I'm going to copy it for us, hopefully, if I can get that to work. So actually, let's delete that and let's just put it in. There we go. So the torque to raise is our friction, our force, our major diameter divided by 2, lead plus pi, there's our friction coefficient that we have up here. Major diameter times secant alpha. Remember, the equation in the book is for a square thread, and the trapezoidal has this angle on it which creates a different friction coefficient. So we have to get the secant of that. Oh, you know what? I didn't put the secant on this part also. I just now noticed that. There we go. So that'll change our numbers a little bit from what I had. Actually, it didn't change it at all, did it? I guess the secant of 15 degrees is pretty small, or pretty close to 1, rather. All right, so there we have our modified equation for torque to raise, modified in the sense that we included the angle of the threads. I'm just checking to make sure I put everything in the right spot, since I hadn't noticed that before, but I'm pretty sure this is where it goes. Yes, it is. All right. So 0.032 Newton meters, so not a lot. That's pretty low. Torque to lower, well, I also already created this equation, so let's see if we can cut and paste it. Torque to lower, same thing there. I didn't include the secant alpha. There we go. Again, it doesn't really change it though. We have the force that we're lifting from the mass of the gantry. We have the major diameter of the lead screw. We have pi, friction coefficients, We have the major diameter minus the lead. This is the one that can also tell us if we have self-lowering or self-locking rather, or lowering in this case. We did end up with a negative torque to lower, negative 0.007. So it's, essentially zero, but it is negative. And I can tell you that when you turn the power on these, they don't immediately drop, but it does not take a lot of force to applied pushing down on the gantry to make them lower. And so this, I can believe this number. The rest of the reason why it's not automatically just dropping, I actually do have one printer that would drop if you didn't be careful about turning it off, already lowered. But there is a little bit of friction in the stepper motor itself. So the stepper motor takes some amount of torque, even when it's off, to step over to the next step. And it's a tiny amount, but it is apparently enough to overcome this negative torque to lower, because they don't automatically just drop, but it doesn't take much to make them lower. So this number seems believable to me. All right, so let's talk about, now we have torque to raise and torque to lower. Let's see how much power it's going to take to raise this at the maximum speed that we want to raise it. So let's institute a variable, max z feed rate. So in your slicer and your firmware, you can set maximum feed rates for X, Y, Z, the different directions. Let's put this one, I know that in one of my slicers, it's set to 12 millimeters per second. So that's pretty slow. That's more like when you're printing, but let's just go with that for now. And then this is the nice thing about setting these things into MathCAD, is that we can change any of these variables and see what their effects are on the whole system. So let's do 12 millimeters per second. Let's define how much a turn is. So one turn is 2 radians, so that we can have our radians in there. Because what we're trying to solve is power equals torque times omega. We just found the torque to raise it anyway. And the torque to raise is greater than the torque to lower, so I'm more interested in being able to raise the z-axis quickly so that I'm doing the z-hop command. So 12 millimeters a second is not terribly fast. I'm sure we can go much faster than that. In fact, we can get a theoretical maximum based on our hardware here in a second. So omega, so this is the angular velocity of the shaft that we're turning, is going to equal our maximum z feed rate, so how fast we want to go, divided by our leads per turn. So our lead per turn. So we have an 8 millimeter lead, so every turn gives us 8 millimeters. We want to go 12 millimeters per second. This will tell us how many, what our angular velocity, or radians per second, are going to be. So 9.4 radians per second angular velocity. And now we can do power equals, let's just call it this, torque to raise. Whoops, I used a capital T. Torque to raise times this omega angular velocity, and it's 1/3 of a watt, so not a lot. That's pretty low. I suspect our system is capable of producing 1/3 of a watt of power in that stepper motor. In fact, we can calculate our stepper motor theoretical. Let's call this our theoretical stepper motor, or stepper power. We're not going to actually go measure this. We could hook up multimeters and get the current and the voltage to go into these stepper motors and try to figure out what the actual power is. We're just going to do our theoretical power. So like I said, this is for a NEMA 17. There's 3 different styles. There is a low power, so a pancake one. There's the normal one that we have here, and then there's a extra torque, which is even longer. So basically they just put more magnets and more coil in the extra heavy duty one, and less of that in the pancake one. We have the NEMA 17, we'll call it normal. What's my, uh-oh, where did MathCad go? I think it might have crashed, but fortunately I have another one. So let's just look at this MathCad. All right, so here's where we were. Let's save this just in case we crash again. I don't know what caused it to crash. All right, so like I said, we have our theoretical stepper power, and it's not measured. So if you go look up a Creality NEMA 17 stepper motor, it lists the nominal voltage as around 4.8 volts. So again, I didn't measure that, but that's what it's listed as. And then if you have the TMC 2208 driver, so these are the little drivers inside the printer that control the stepper motors. If you have those, they have a maximum current of 1.2 amps that they can deliver. So power, electrical power, is voltage times current. So it looks like we can generate almost 6 watts of power, and we needed, oh wait, this doesn't have the same numbers. This is at 200. All right, so we were at 12 millimeters per second, weren't we? And we're still on the same, yeah. We needed 1/3 of a watt. We can generate almost 6 watts, so we're pretty good there. Most electrical motors, though, are around 80% efficient, so maybe we really only have around a max of 4.6 watts. Still plenty to drive our 0.3 watts. Do we have enough torque? So, same site to get the specifications from that NEMA 17 motor. The torque that is listed is 40 Newton centimeters. We needed 3 Newton centimeters, 0.032 Newton meters. Oh, this one, while we're here, let's fix this, since this one doesn't have the secant alpha on there. Oh, I didn't put the multiply. There we go. There we go. All right, now it's more correct than it was before. All right, so we have plenty of torque. Here are our stress calculations. So this is sigma x. Remember, we're doing the stress. Let's see if we can look at this. It's going to be really tiny, so let's zoom in some, as much as we can. Well, we can zoom in a lot. Gets a little blurry at that level, though. So we're trying to do the stress at the root down inside there, at the root of one of these threads on the top side, where it's bending in tension. So where are we at? There we are. Somewhere inside there. It's hard to do this. There we go. Down in there, where the very tip of that is pointing. So that's what we're doing. So our sigma x is, remember, we're creating a stress block. Let's draw that again, since it was in the other video. Let's zoom out some, get that out of the way. We are creating a 3-dimensional stress block cube with, there it is, kind of blurry though. There we go. So there's our cube. Sigma x is here. That's the one we just calculated here, and it turns out, not even 1 megapascals. So this is, we did use the 0.38 F, so the 38% of the force on one thread. Remember, this equation normally is 6 times F over pi dr number of threads times P, and we just took that worst case with the one thread that has 38% of the load. It has the most percentage of the load. And so we did do that analysis here, which still gives us less than a megapascal. That's sigma x. Sigma y is a compressive force. This is basically the weight of the gantry, pushing back down on this block. and we did that calculation, it's just P over A, or force over area. And the area is the circle that makes up the root diameter here. It is a negative because it's compressive. Half a megapascal, not even half a megapascal. And then we have our tau yz, and there would be one on the bottom down here also. Don't really have a good way to draw that, but it's down there. And this is the torsional shear stress right here. And they give an equation in your book, 16 times the torque to raise pi dr cubed. So it's TC over J type equation. Again, half a megapascal. The others are 0. So there's no sigma z, and there's no shear stress on either of these faces. So those are all zeros. At that point, once you have sigma x, sigma y, the values of 0 for the other stresses that we just don't have on here, you could do one of two things. You could go do your von Mises combined stress, or you could create a Mohr circle. So either one you want to do. I did both. So von Mises will give us the combined stress on the worst possible orientation for this cube, and it's 1.4 megapascals. I did look it up, and stainless steel has a yield strength around 200 megapascals, so we're nowhere near. We're nowhere near the yield strength of the stainless steel, which we would expect. These 8mm metal rods should not fail because it's lifting a tiny little printer's gantry. This does give us the Tresca maximum shear stress up here, just over 0.75. It ended up being 0.795 megapascals for the maximum shear stress. There's that von Mises again, the same number that we calculated the other way. So again, we're nowhere near the shear strength of stainless steel either, so we're fine on the stress. Where we're getting kind of close is I was taking a very conservative 12 millimeters per second here. And I was needing 1/3 of a watt. What if I really wanted to speed this up? What can I speed up to? So 120 millimeters per second. Some of the X and Y axis, their max is, much higher. It could, for a regular printer even, it's going to be in the 200 millimeter, 500 millimeter per second. If you have some special boards, controller boards, then you can go theoretically higher than that, assuming your steppers and drivers can handle that. So 120 millimeters per second doesn't change any of the torque to raise or lower, but now we want to do all this faster. Now I want to spin this at 94 radians per second. Now I need 3 watts of power to do that, which, my estimates here are that I could probably predict 4.5 watts of deliverable power for that z-axis, assuming that I have the current supply to do that, to spread it out over the X, Y, Z. They're all moving at the same time. The extruder's moving, it's drawing current as well. So assuming I have enough current in the whole system, then I should be able to deliver 4.5 watts. And now I'm getting at 3 watts. None of these actual stress numbers change. It's just the power to actually do the moving, which is dependent on how fast I want to apply this torque to raise. So it looks like I could do 120. Can I do 150? 3.8. I'm getting closer here. I think I had 200 millimeters per second here, and I couldn't do that. Yeah, that needs 5 watts, and I theoretically have 5.8 watts, but knowing that most motors are around 80% efficient, I probably could only get 4.5 watts or so. And at that point, I would potentially not be able to supply enough power to actually do the motion that I called for. And what would happen then, these motors, these stepper motors on this printer, don't have any feedback system that lets them know they didn't do what you told them to do. So I could very easily get some shifting in the print. If it thought it raised 8 millimeters, but it really didn't have enough power to get all of that done in that amount of time, and it only raised 7.5 millimeters. I'm suddenly a half millimeter off in its tracking, and it doesn't know that. It doesn't know it didn't deliver that motion. So there are, rules. There are limits on these kind of things. These are practical. In this case, we didn't really need to do the stress calculations, even though it is practical on this particular application, because we're nowhere near the stressing points of the steel that we're trying to do. But this is how you would do them on something that is going to be pushed closer to the limit. Other things you have to consider that we didn't look at here are these columns, the column created by the lead screw. So it ends up being a column, and it's relatively thin, so it might fall under a buckling category that we have to look at even. So, you could imagine a very long, thin column like this with an axial compressive force on it that's large enough could cause it to buckle. So you do have to worry about those things also. Again, in this particular scenario, we wouldn't have to worry with that. But this does let us go in and figure out what our theoretical maximum feed rate is for the z-axis. So it looks like it's somewhere around 180 maybe. Yeah, somewhere around 180 millimeters per second is our theoretical maximum feed rate without the system failing, as far as not delivering the movements we asked for. Now, is it ever going to move that fast? Actually, probably not. Not the Z anyway. The X and Y, maybe they could theoretically move that fast, practically move that fast, but the Z usually doesn't. But at least now we have a number that is founded in the mechanics of what's going on, the electrical power we have available, and the mechanism itself. And these are the type of things that we can do in our machine element design knowledge. All right, so I hope that helped explain some of the equations in power and lead screws, and that makes it a little clearer what everything is doing and how you might use one of these things. Also, I just noticed here, our torque to raise is 3 Newton centimeters. Well, I think I mentioned that before, but the motor itself does have a torque that it can deliver, but it was way more than that, like 40 Newton centimeters or so. So we're not getting worried there either. All right, I just am going to post this for a little extra walkthrough of how these equations actually get used in a practical way. See you next time.